U-Substitution. So U-Substitution is primarily a technique that is used in finding integrals, in the sense, if the integral follows a specific pattern, then we could use U-Substitution to integrate it. But keep in mind, it has to satisfy a certain pattern. So let's say we have an integral of that sort. How would you go about integrating it? One way of doing it is to FOIL everything. So I'll call this method 1. I distributed the 2x inside, then I'm going to integrate each term that is inside the integral. So I would get 2x raised 4 over 4 plus 2x squared over 2. So the 2 and the 4 would get cancelled. The 2 and the 2 would get cancelled. So we would end up having x raised 4 plus x squared and x raised 4 over 2 plus x squared. And if you take a common denominator, this would become x raised 4 over 2 plus 2x squared over 2. So we have a common denominator, which is 2. I have an x squared in common in the numerator, so I could pull that out and write it as x squared multiplied by x squared plus 2 divided by 2. As I mentioned last time, I'd like to add the constant of integration at the very last step. And that is method 1, and I did not use U-Substitution. Method 2 is U-Substitution, and it would play a role in certain problems. I will show you an example, and in some cases, the only way to do the problem is to do U-Substitution. That is our given integral. And I'm going to rearrange things so that you can understand it better, but it's not necessary, but I'm going to rearrange it and write it as x squared plus 1 multiplied by 2x dx. Why do we call it U-Substitution? You pick one of these two terms and set it equal to u. But whatever you select for u, when you differentiate it, you get the other term that's in the integral. So I have two terms. That's term 1. That's term 2. We can leave that dx part as this for now. Now ask the question, what should u be? If u is x squared plus 1, would you get 2x?
What did you say? I'm sorry.
If I set u to be x squared plus 1, if I take the derivative, would I get 2x?
Yes.
Yes. But if I set u as 2x, would I get x squared plus 1 when I take the derivative?
No.
No, because that would be 2. So of the two terms, u has to be x squared plus 1. So let u equals x squared plus 1. Now the dependent variable is u and the independent variable is x. So I want to take the derivative of u with respect to x. So du over dx is equal to 2x. Multiplied by dx on both sides, we'd end up getting du equals 2x dx. So by carefully choosing u, when I took the derivative, I got the remaining part of the integral, which is 2x dx. If you pick the wrong u, then you're going to end up in trouble. So you've got to always ask the question, whatever u that I pick, when I take the derivative, does it give me the other part of the integral? In this case, it does. So I'm going to take the original integral that is in terms of x's, and I'm going to rewrite it in terms of u. X squared plus 1 would be u. So that part is what I call as u. 2x dx is the du part, whatever that is left over. So I'll have du. Now the power of u is 1. So when I integrate it, I'm going to get u squared over 2. Yes? But what is x? X is, what is u? U is just x squared plus 1. So I could write it as x squared plus 1 squared over 2. Are we clear? Now this answer doesn't look anything like that answer, right? So something seems to be off. Maybe we just have to factor FOIL and see if everything works out. We didn't do anything wrong. So if I FOIL the numerator, I will get x raised 4 plus 2x squared plus 1 over 2. Yes? That would equal to x squared times x squared plus 2 over 2 plus 1/2. Yes? I split it up. Plus c. But a constant plus 1/2 is still a constant, correct? So I'll just call it C1. And you can see that this matches with that. So care must be taken in choosing the value of u, or choosing the expression u. If you pick the wrong one, then you won't get to the correct answer. So, of course, I could FOIL this and try to come up with an answer, but do you really want to FOIL this stuff? I mean, this is not that difficult. The next problem, I'll make it really challenging. So, we can FOIL and integrate them separately. Now I ask you, well, of the two expressions, which one should be u? Should u be 3x squared plus 2? Or should u be x cubed plus 2x? Keep in mind, whatever u that you take, when you take the derivative, it has to give you the other expression. Wait. Expression 1, expression 2. If I pick u as 3x squared plus 2, when I differentiate it, would I get that term? No. If I pick this as u, when I differentiate it, would I get that term? Yes. So I'm going to call u to be x cubed plus 2x. Then du over dx would be equal to 3x squared plus 2. Yes? If I rewrite it, I'd get du is equal to 3x squared plus 2 times dx. And the next step is where I rewrite the integral. So the original integral that was in terms of x now can be written in terms of u. X cubed plus 2x is u. The remaining term, 3x squared plus 2 multiplied by dx, is simply du. If I integrate u du, I know the answer is u squared over 2. And don't leave the answer as is. We have substituted u to be equal to x cubed plus 2x. So we've got to go back and plug in the substitution. Which would give me x cubed plus 2x whole squared divided by 2. You can leave that as is, or recognize that x is in common. So if I pull x out of the square term, what is going to come out? If I pull the common factor x, that's between x cubed and x, outside of the square, what will I have outside? Just x or x squared?
X squared.
X squared. So I'm pulling x out of the square, so I'd end up having x squared and x squared plus 2 squared over 2. I'm going to throw in the constant at the very last step. Does that make sense? Good so far? Now, here is a problem where you absolutely have to use U-Substitution, or else you are going to get stuck. Of course, as always, like the last two problems, A and B, I could FOIL, do you really want to sit and FOIL x raised 4 plus 7 raised 15?
No.
Absolutely not. It's a waste of time. So this is a type of problem where U-substitution will play a crucial role. Now, of the two expressions that I have, one is 4x cubed, and the other is x raised 4 plus 7 raised to the power of 15. I'll have to pick one of them as U. Should that be U, or should that be U?
2.
That. Because if I differentiate it, I'm going to get that. So U has to be x raised 4 plus 7, which would imply du over dx is 4x cubed. Therefore, du would be 4x cubed multiplied by dx. And that is the remaining part of the integral. So I could replace 4x cubed times dx by du. So the integral that we started in terms of x can now be written in terms of u. I called x raised 4 plus 7 as u. So I will get u raised 15. The remaining 4x cubed dx is simply du. And we all know how to integrate u raised 15 du, yes? Usual power rule. The power here is 15. So what would I get by integrating?
15 u to the 14th power.
That's taking the derivative.
JK.
U raised
16.
16 over 16. I had to mention the video for last time is still being processed, so the video from Monday and the video from today will be posted today. Don't leave the answer as is, you've got to rewrite it in terms of x, so x raised 4 plus 7 raised 16 over 16 plus c. So which is easier, using U-substitution or sitting and foiling everything and taking the integral? If you've got nothing else to do, go for this, right? But we all have something else to do always. So in a problem like this, it is very important to think of U-substitution. But then again, there are cases where you may have an expression like this, but this term could be missing. You don't have to worry about it in this class. As far as this class is concerned, in this particular section, anytime you choose something as u, the remaining part of the integral will have du in it. Does that make sense? Okay. Can I erase this? I'll let you try one. Previous problem, we don't want to FOIL because it is going to take forever. Consider this problem. We have a radical. If we have a radical, the first step that we do when it comes to integration is write it in terms of a power. So 2x multiplied by x squared plus 9 raised 1 over 2 dx. Correct? Now, is it possible for me to distribute that inside and then take the integral? Would it be an easy task to do?
No.
No, it is not going to be, because is it possible to move this term inside? Absolutely. But could we integrate it directly based on the knowledge that you have in this class? No. So we have to use U-Substitution. So I'm going to give you a few minutes, pick the appropriate U, and use power rule to integrate, and let's see if you can get the correct answer. What should U be?
X squared plus 9.
X squared plus 9. So if U is x squared plus 9, du over dx would be 2x. Yes. So du would be equal to 2x dx. So if I set that to be u, I get the remaining part of the integral. So I could rewrite the integral as u raised 1/2. The remaining part of the integral is simply du. And what is the integral of u raised 1/2? It is u raised 1/2 plus 1 divided by 1/2 plus 1, which is 3 over 2. And you could flip and multiply. You would have 2 over 3, u raised 3 over 2. Are we done yet? No. You've got to replace u by the x squared term. And throw in the constant at the very last step. Does that make sense? Good. Can I erase? What should u be? Not so obvious in this problem. If you go back and look at every single problem that we did, A through D, it was pretty obvious because I made it so. What about this problem? Could u be x squared? Definitely not, because if I took the derivative of x squared, I'm not going to get x cubed plus x plus 1. It's not going to happen. So u has to be x cubed plus x plus 1. What is the derivative of u? It is 3x squared plus 1. Yes. If I rewrite it, I would end up getting 3x squared plus 1 times dx. correct? And you look at that and you say, well, I don't see anything relevant to just x squared, right? But we may have to just solve for x squared. Or we can use a trick here. What is the trick? I'm simply going to multiply and divide by 3. Did I do anything wrong? No. So I could pull 1/3 out. And that would be the integral. I want you to take a minute and see if you can solve that. Okay. So clearly I can't replace dx as is, right? So what I can do, I could rewrite it, oh, clearly we can't rewrite 3x squared dx as is. So what I can do is rewrite dx in terms of du. So dx would be equal to du over 3x squared plus 1. Yes? Now that would be x cubed plus x plus 1 cubed 3x squared. If you replace, you will get du over 3x squared plus 1. It still hasn't helped much. So we've got to do another trick here. What I'm going to do is I'm going to add and subtract 1. Did I do anything wrong algebraically? Just by adding and subtracting 1. What is 1 minus 1?
0.
0. So I didn't do anything, I just added 3x squared by 0. Now what I'm going to do next, I'm going to treat those two as separate factors. I'm going to distribute. If you understand this problem, you would have mastered U-Substitution. So do watch the video over and over if you have to. So I'm going to distribute that in. When I distribute this term multiplied by that term multiplied by that 1, I will end up getting integral x cubed plus x plus 1 cubed 3x squared plus 1 du over 3x squared plus 1 minus integral x cubed plus x plus 1 cubed du divided by 3x squared plus 1. Good so far? With me? Yes? So, that is u. Right, that's u. Yes? And that would be down. It may not work. Let's see. Those two would get cancelled. Get u cubed du. Okay, let's take a look at the first integral. So the first integral would be integral u cubed. The 3x squared plus 1 would go away. I'd simply have du. The second integral ends up having x cubed plus x plus 1 cubed over 3x squared plus 1. U is simply x cubed plus x plus 1. And I would have du over 3x squared plus 1 as just dx. What is u cubed du?
X cubed plus x plus 1.
Yes?
And then wouldn't du be what you put down there for the 3x squared plus 1 dx?
That one?
Okay, forget I said that.
So I've replaced this as u. And I have du over 3x squared plus 1. But du over 3x squared plus 1 is dx. The most common mistake would be to treat u cubed as a constant and pull it out of the integral. But u is not a constant. U depends on the x terms, agreed. So we would have to go back and do x cubed plus x plus 1 cubed dx. So all of that would equal to, what did we have? Integral x cubed plus x plus 1 cubed multiplied by what? 3x squared. Yes?
Yeah.
Good. That integral, I have minus 1/3. Oh, I'll just keep it as this. This should be at that 1/3. So 1/3 first term minus 1/3 integral x cubed plus x plus 1 cubed dx. Good so far? Going to move this term to the other side, when I move that term to the other side, I would have plus 1/3 integral x cubed plus x plus 1 cubed dx. Yes? And that would equal to 1/3 and that would be the right hand side. Good so far? If I combine those two, I would have x cubed plus x plus 1 cubed. That's the common term, and I could write it as 3x squared plus 1/3 dx. And that would equal to 1/3 x cubed plus x plus 1 raised 4 over 4. We still need a reasonable, u on this side. What should we pick for u now? On this side, if I pick u as x cubed plus x plus 1, I'm just going to get 3x squared plus 1. So could we rewrite that in terms of 3x squared plus 1? Three x squared plus 1/3 somehow. So I'm trying to make a point here. So if you pick u to be x cubed plus x plus 1, you end up getting 3x squared plus 1. But what we have here is 3x squared plus 1/3, right? If we do an algebraic trick at this step, and you said, okay, I could write that 1/3 as 1 minus 2/3, and then do a substitution, you would still end up getting another term, minus 2/3 and x cubed plus x plus 1 cubed. So in this problem, no matter how hard you try, you would be going in circles. Because the very first integral that we started with after the first substitution resulted in that integral, and that integral ended up having whatever substitution that we used. So when we rewrote it, moved to the other side, and we ended up getting that, even if you split it up and rewrite it, we can integrate it, but we cannot use U-substitution directly. Does that make sense? Because no matter how hard you try, you're going to keep on going in circles. So this particular problem is a good illustration on choosing u and du, but unless you can definitely come up with the remaining part of the integral, you will just keep on going in circles. Does that make sense? I'll do one more where you don't have the exact u, but we can rewrite it and get these. So as far as this problem is concerned, could we integrate it? Yes. But can you do it based on the knowledge in this class? No. Because you'll be going in circles. I'll do one more problem to illustrate my last point. What is this, f?
Yeah.
So you have x times 3x squared plus 1 raised 4 dx. What should u be?
Technically, it should be the 3x squared plus 1.
U should be equal to 3x squared plus 1. If you take the derivative, you get du over dx equals 6x. Yes? And if you multiply, du is equal to 6x dx. Correct? So, go back to problems A through D. All those problems had the exact term in the integral. Yes? Problem E, the last one that we did, it didn't have, and we tried to do a bit of algebra, but we kept going in circles. And you look at this problem and say, whoa, I don't see anything exactly that resembles 6x dx. Do you see that over there? No. Do you believe that we're going to go in circles like it happened in the previous problem?
Not as many.
Huh?
I said not as many, because you still have to get the 6 from somewhere.
We still have to get that 6 somewhere. The moment we got that 6 somewhere, we should be okay. Remember the very first step that I did as a trick in the previous problem? Multiplied and divided by 3. Correct? I'm going to multiply and divide by 6. Move the 6 inside, so I'll have 1 over 6 integral 6x multiplied by 3x squared plus 1 raised 4 dx. Did we get the 6x dx part? That we very much needed, yes. So that would give us 1 over 6 integral 3x squared plus 1 raised 4 would be simply u raised 4. The 6x dx would be du. And we know how to integrate u raised 4. It is simply u raised 5 over 5. But are we done yet? No, we have to plug the u back in. So 6 times 5 is 30, multiplied by 3x squared plus 1 raised 5 plus c. Does that make sense? So, A through D, it was very easy because the du part was directly available in the integral itself. Problem E, I used it to demonstrate that sometimes U-substitution, even if you see part of it, and even if you do algebra, you'll be going in circles because things have to fall in place. Here, you didn't see the exact 6x in the integral, just like the previous problem. We didn't see the du part directly, but it was just multiplied by a simple constant. So if I somehow introduce that 6, I use the trick 6 over 6, just like I did 3 over 3 in the previous problem, and then I was able to complete U-substitution and integration. Does that make sense? So as far as this class is concerned, you're not going to encounter a problem like part E. I did it to demonstrate that sometimes, no matter what trick you employ, you may go in circles when it comes to U-substitution. So choosing the substitution and manipulating the algebra properly is very key to completing a problem in U-substitution. Does that make sense? Yes? Okay.